So far we've dealt with some fairly intuitive concepts around exponents, some relationships that result from our definition of the exponent. So we've looked at the special things that happen when we multiply powers, when we divide them, when we raise one power to another power. And, so when we look at something like h to the power of 92, for example, you know, it might be a very large number, it might not be a number that we can compute off the top of our heads, but the idea of it makes sense, right? H to the power of 92 is 92 eighths being multiplied together. And even 2 to the power of 1 was a bit of a stretch for our minds, but not too far of a stretch. 2 to the power of 1 is just a single 2, not being multiplied with anything else. It's just a single 2 by itself, or any number to the power of 1 is just that number itself, not being multiplied with anything else, and so on. And I think that exponent of 1 was so far the only slightly uncomfortable thing that our brains had to sit with, but even then, not completely wacky. Now we begin to look at some interesting consequences of our definition for an exponent and some of the relationships that we established between powers. So, the multiplication, division, and the special things that happen when we perform those operations on powers. And we're going to look first at the first peculiar thing, which is a zero exponent. So when I write something like 5 to the power of 0, what does that mean? And also importantly, what is the value of an expression like that? So let's unpack this in a number of different ways. So forget I mentioned an exponent of 0, and let's look at this quotient over here, 5 to the 12 divided by 5 to the 12. So first off, let's look at it in what I think is the most straightforward way. 5 to the 12 divided by itself, well, any number divided by itself is 1, right? So 3 divided by 3 is 1. 100 divided by 100 is 1. A million divided by a million is 1. 5 to the power of 12 divided by 5 to the power of 12 would just be 1. Or another way we could look at it is if we were to expand the powers, then this would be 5 times 5 times, okay, so 12 fives multiplied together, divided by another 12 fives multiplied together. And what we saw in a previous example was that, these begin to cancel out with one another. So that cancels out with that. 5 goes into 5 ones, 5 goes into 5 ones. And it's very important to remember that when these 5s cancel, they're not leaving zeros, right? We're saying 5 goes into itself once. 5 divided by 5 is 1. 5 divided by 5 is 1. 5 divided by 5 is 1, and so on. And so what we're left with is 1 times 1 times 1 times 1 times 1. 12 ones multiplied together is still just one big old 1. So that's another way that we can think about that quotient. But what about using the relationship that we saw between powers, so when we divided powers with the same base in a previous lesson? So we saw that, for example, if we had 2 to the power of 8 divided by 2 to the power of 6, then that was the same as 2 to the power of 8 minus 6, which is 2 to the power of 2. And so 5 to the power of 12 divided by 5 to the power of 12 is 5 to the 12 minus 12, which is 5 to the 0, right? And so that, so there appears that little strange thing, the exponent 0. And what we've seen from the other ways that we've explored this quotient is that this quotient is equal to 1, right? And so that would mean that an exponent of 0 makes a power equal to 1. And so, in general, what we can say is a number to the power of 0 is the same as a number to the power of m minus m, right? We agree that m minus m is 0. So whether that m is 12, so 12 minus 12, or 100 minus 100, or 20 minus 20, it gives you 0. But we know that when we subtract exponents, that's the same as dividing two powers, right? So a to the m over a to the m, right? We agree that this and this are the same thing, right? And a to the m divided by a to the m is just the same as 1, which means that any number to the power of 0, we'll talk about an exception just now, is just equal to 1. So 5 to the 0 is 1. 100 to the power of 0 is 1. A to the power of 0 is 1, and so on. Okay? And the exception over here, can you think of an exception? So what value of A would break this whole system of ours? Well, if A was equal to 0, then we'd be in a bit of a mess, because then we'd be dividing by 0 to the power of m, and 0 to the power of anything is just 0, right? No matter how many zeros you multiply together, you're still just going to get 0. And dividing by 0 is undefined in mathematics. So in general, yes, any number to the power of 0 is equal to 1, except if that number is 0. So 0 to the power of 0 is something whose value we do not know, right? So let's practice using this knowledge quickly. So 5, so let's say we had to simplify the expression 5, a to the 0 b squared, right? So that would be equal to 5 times a to the 0 is just 1 times b squared, and that would just be 5b squared. Anything times by 1 is just itself, right? Another example, 3a squared b to the 5, all raised to the power of 0. So I mean, you could say, well, I'm raising all of this to the power of 0, so 3 to the 0 times a to the 2 times 0 times b to the 5 times 0, because remember, when you raise a power to another power, you multiply the exponents. So you could do it that way. You could say this is 3 to the 0 times a to the 2 times 0 times b to the 5 times 0, and 2 times 0 just ends up being 0, and 5 times 0 just ends up being 0. And so you've got 3 to the 0, so you've got 3 to the 0, which is 1, times a to the 0, which is 1, times b to the 0, which is also 1, and so your product ends up being 1. So you could do it that way, quite painstaking, or you could recognize that anything to the power of 0, anything, no matter how complex it is, anything to the power of 0 is 1. So this whole thing is being raised to the power of 0, which means that its value is 1.